Right, guys. So I'll move on a bit sharpish. So welcome to today's BIS West Midlands talks. Program is as usual. Quick welcome from me, and then we'll hand over to Christopher MacLeod to talk for his talk, and then there'll be the session will be open for questions at the end. So big announcements, really good announcements. BIS headquarters, the council have come up with a new set of guidelines for branches. Hopefully this is going to make the branches much easier to run, and hopefully we'll get more branches being started. So what we will find is, if you look in the chat on this on Zoom, you will find a BIS newsletter which contains the information for the branches. So by all means, download that, have a look at it, and it's also, as I said, the BIS brand new West Midlands branch first ever newsletter, another innovation that's being allowed now. So that's good news. So we're also going to be allowed our own mailing list, so we'll be able to contact people and we can have finances. Yeehaw! So if you would like to help start a new branch, by all means, use that email there and contact branches@bispace.com, and that is Robin Brand, the council member for branches, and he'll be very pleased to hear from you. So I'm hoping that this should give the branches a bit of a kickstart. So and same for if you'd like to get in touch with us, be a member of the West Midlands branch or help us run the branch, do get in touch. Do keep an eye out for the online socials that headquarters run. And of course, there's lots of things, that benefits for joining the BIS. Please do look on the website and have a look round. There's lots of stuff, very interesting and useful stuff. And please join the British Interplanetary Society. We need you. So we're always looking for articles for the magazines, JBIS, Space Chronicle and Spaceflight. And of course, there is now website articles. Fabrizio from the Italian branch has been very keen to get this up and running. So if you would like, if you don't think that something is appropriate for one of the magazines, by all means send stuff across, and it might go in the website. And with that quick gallop through, I'm going to hand over to Christopher MacLeod. So I'm very much looking forward to this. So bear with me while I try and work out how to stop sharing, because I've forgotten.
Okay, can you hear me and see my screen okay? Yeah, excellent. Thanks very much. And thanks for all that. So let me start my slideshow and tell you a little bit about what we're doing here. So first of all, my name is Chris MacLeod, and I greetings from the Outer Hebrides, because that's where I am currently from. So I should say greetings Earthlings, because it's like a different planet up here. So let me tell you a little bit about our research here and what we're doing. This is an engine, a little bit like a scramjet engine, and it's basically designed for space planes. So the first couple of slides just explain why we might want this, first of all, and I think most of you will be familiar with these arguments anyway, but I'll just go through them quite briefly. And then it'll go on to just explain how this works and the work that we've been doing. So we all know rocketry is the current go-to technology for getting into orbit. But rockets have quite a lot of issues with them, as I'm sure you're all aware. They're not reusable, and although Elon and others are working on reusability and improving that, there's still a lot of it that's thrown away. They're not particularly reliable. Just the infrastructure of stacking things up for vertical launch costs a lot of money, which leads to the fourth point there, that they're very large, expensive, and require a specialist infrastructure. But one of the biggest problems, and in fact, what leads to all these issues in the first place, is that they have to carry all their oxygen with them, or all their oxidizer, I should say. It doesn't necessarily have to be oxygen. If they're a hydrogen powered rocket, as we would like, because it's less polluting, they've got to carry up to 8 times their mass in oxygen compared to their actual fuel, hydrogen. And if it's some other type of fuel like kerosene or one of the other hydrocarbons, then it's up to about 4 times more. In fact, these figures are slightly different because engines tend to burn a slightly rich mixture, so it's not quite as bad as that. But those are what we call the stoichiometric ratios, the actual ratios which are used in theory. So what we would really like is an air-breathing engine, because as the vehicle is going up through the atmosphere, it's surrounded by abundant air which contains oxygen. And if you could take away that enormous weight deficit of having to carry up to 8 times more weight of oxygen or oxidizer than fuel, then you could get a whole lot of benefits. Like it might be much more like a plane. It might be a multi-stage plane, a bit like sort of Virgin Galactic, where you've got a carrier that drops the rocket and then, or drops the vehicle. But it could take off and land on a horizontal surface like a conventional runway. And there are benefits of that, like reusability. You can land the thing more reliably back and all that sort of stuff. But also, if you are talking about a horizontal takeoff and landing aircraft, you can start to compare it with the safety record and the costs of conventional aircraft. And if you work out how much fuel is required to reach orbit and stuff like that, in theory, after development, it should cost about as much to get into space as a trip to the other side of the world, like Australia or New Zealand. So those are the benefits, which I'm sure you all know anyway. So the leading contender for an air-breathing engine is a scramjet. And scramjet engines, I think the next slide just gives you a quick overview of them. Despite what the US government say and NASA says, no one's ever got one to work really satisfactorily. You'll read articles saying, oh, there's been a burn for this much and it's produced thrust. If you look at the data, that's a bit of an optimistic view of actually what's happened. And the main reason they don't work is that, well, there's 2 big reasons. One is drag. At these speeds, you've got an enormous amount of drag. You're talking orbital velocity is over 20 times the speed of sound. So by the time you've reached that velocity, there's a huge amount of drag. Of course, the last bit of that is essentially in an airless environment, so it's not quite as bad as it sounds, but even at the lower speeds, there's huge amounts of drag. But one of the main reasons is that the air has got to go through the entire engine in just a few milliseconds. And how do you mix the fuel in and burn it within that time? You've actually only got microseconds to mix the fuel properly and to get it to burn in the engine to produce thrust. And not only that, because this has got to be efficient, the air coming into the engine is very hot because you're traveling very quickly. And adding extra heat to it is much more difficult than it is at lower speeds because it's already an energized hot airflow. And so burning fuel in it is adding a sort of minimal amount of extra energy to the flow. So it has to be a very efficient burning process. So you've got these twin whammies of getting the stuff to mix and the fuel to mix with the air, and then burning it within the amount of time and getting it to mix efficiently. So that is the reason that they don't work primarily, is that mixture. And what actually happens is when you see it in an actual wind tunnel, and you'll see this a little bit later in the presentation, the air just blows the fuel away. There's all sorts of technical, complicated equations to describe this, and simulations and computational fluid dynamics, CFD simulations and stuff. But when you actually see it in reality, there's this enormous speed of air coming in, somebody injects fuel in, and the fuel just blows away, essentially. So if you're not familiar with how a scramjet works, let me just explain that a little bit. In a conventional jet engine, like the one you can see on the top right there of the slide, the air is sucked in and compressed by a series of fans, essentially, compressors. Then fuel is added and burnt, and the hot air stream passes through the turbines on the way out, which in turn turn the fans at the beginning, the compressor, to suck more air in. This works well below the speed of sound, and you can force it to work up to about 2 or 3 times the speed of sound by having a duct in front of the engine which slows the air down to below the speed of sound, to subsonic speeds. So in a fighter jet, for example, that's like a Tornado or something like that, that's going twice the speed of sound, the engine itself is still working below the speed of sound, subsonically, but there's a duct at the beginning which is slowing stuff down before it gets into the engine. And the problem is you can't have air going in supersonically, because these fans generate shock waves and they would just shake themselves to bits, essentially, if that happened. Now, fortunately, once you're traveling at a certain speed, the air itself is rushing towards you at such speed that it will literally, you don't need the fans anymore. It will ram itself into the engine. And that is the middle picture on the right there, which is what we call a ramjet, which I think you're probably familiar with as well. In ramjets, there's no moving parts. We've taken away the fans at the beginning. The air is moving now so quickly that it's just ramming itself into the engine. Again, we just add fuel, we burn it, the hot gases expand through the nozzle, producing thrust.